Hey guys, hope everybody's doing okay. This is the first lecture in a series of 3 where we're going to talk through chapter 17, which is all about equilibrium. Okay, so the first section in chapter 17 is about reaction rates and equilibrium. Okay, and 17.1 is more conceptual. And then next section 17.2 is where we'll start to kind of apply some quantitative analysis to the concepts that we talk about in today's. Okay, so before we talk really about equilibrium, I want to back up and kind of frame what's happening in equilibrium and kind of get some concepts under our belt that we need to understand that. So we first need to discuss, how do chemical reactions occur? Okay, how do they occur? So we have this idea in chemistry called the collision model. Okay, so this is a model of how chemical reactions occur that's based on the idea that reactions occur during molecular collisions. Okay, so what that means is if you have reactants, you need to, those particles of those reactants are moving around, and when they collide with each other, that is when we get products being produced. Okay, the products form when those reactant particles collide with one another. Okay, if they never come into contact with each other, if there is no collision, if those molecules don't collide appropriately, you will not have a reaction occur, okay, and you won't form any product. So there needs to be a collision present. Okay, and so the way that this works is some of those collisions are strong enough or violent enough, or they produce enough energy that the bonds of your reactants will be broken. Okay, the bonds in those molecules of your reactants will break, and then those reactant atoms will rearrange to form products. So you'll form new bonds that look more like the products of that chemical reaction. Okay, so for example, if we have this reaction, don't worry about those arrows for now, we'll talk about that shortly. Okay, but if we have this reaction, two of our reactants produce one nitrogen monoxide and bromine gas. Okay, if this is our kind of diagram of what's happening, we can look at each one of these steps and explain it using this idea of collisions. Okay, so in that first part of this picture, we see you've got two of our reactant molecules approaching each other at high speeds, right? Because remember, particles tend to move quickly, especially in the gaseous state. Okay, so those two molecules approach each other at high speeds, they collide with each other. Okay, and when that collision is strong enough, it breaks the bonds between the bromine and the nitrogen atom. Okay, so it's kicking out two bromines. Okay, and then we get a bond forming between those two bromine atoms that get kicked out. Okay, so then we end up with final products, two nitrogen monoxide and bromine. Okay, but you can see really what happens there is the bonds break in a certain way in the reactants and they form in a certain way in the products, and that's all because your reactants collided with one another. Okay, so a little bit more about what has to happen with that collision, because sometimes you'll get two molecules that collide, but they don't always react. Okay, so in order to get a collision that's good enough to produce a chemical reaction, we need to meet 3 criteria, or there's 3 postulates that need to be met for this collision theory to apply and to work. Okay, the first thing is they have to collide. Okay, that's kind of like duh. Okay, if they never collide, they're obviously never going to react with each other. Okay, so the first thing is they have to collide with each other. Okay, second one is they have to collide with a certain amount of energy. Okay, that collision needs to meet a certain energy threshold, which we call the energy of activation. Okay, and we have a whole slide on that coming up. But just know, if two molecules gently bump into each other, sometimes that's not a strong enough collision to break the bonds in your reactants. Okay, so if there's not enough energy when those molecules collide, nothing's going to happen. Okay, and finally, when those molecules collide, they have to be kind of oriented properly. Okay, and this you'll get way more into if you take organic chemistry in college. Okay, I'll talk all about the different orientations that these molecules can have when they collide, but just know that if they're not like lined up properly with each other and they bump into each other, they still might not react, okay, because the molecules have to be oriented a certain way in relation to one another. Okay, so that's collision theory. Okay, so once those molecules collide, there are a few things that are going to determine how fast the reaction occurs, okay, or things that affect the reaction rate. Okay, reactions get faster when the concentrations of your reactants are increased. So think about this. Let's say you have your reactants in a container and you add more and more and more. Okay, then you're going to have an increased number of collisions, right? If you have more collisions happening in your reaction space, okay, more collisions, higher likelihood that they'll collide. They might have more energy, or more of those collisions will contain the energy of activation. Okay, more of those collisions are going to happen with the correct orientation. Okay, when you're increasing the amount of reactants present, you're really just increasing the probability that the collisions will happen appropriately enough to make those products. Okay, if you increase the temperature of your reactants, okay, think about that. Those particles are going to be moving around more quickly. Okay, you'll have more collisions, and each collision will have a higher amount of energy when it happens, right? If they're moving faster and they smack into each other, that collision is going to have more energy associated with it. Okay, so you're going to have more of that process of reactant turning into product. Okay, and finally, it's possible to have what we call a catalyst. I apologize, my video cut off. We'll talk about catalysts in a second. I want to back up and talk about activation energy real quick. Activation energy, also known as the energy of activation, is the amount of energy that is required for a chemical reaction to occur. So in other words, it's that minimum threshold of energy that your reactant molecules need to have when they collide in order to allow those reactant bonds to break and product bonds to form. So now I want to introduce this is what we call an energy diagram. Okay, this is a very common diagram that we see in chemistry. When we get to our unit on thermochemistry, we'll look way more at these, but just to give us a visual of what we're talking about when we say the energy of activation. Okay, you're going to have the reaction progress is shown on the horizontal axis, and on the vertical axis we have energy increasing as you go up. Okay, so there we can see our reactants start out at a certain amount of energy. Our products have a lower amount of energy, but in order to get those reactants to turn into products, we can see there's kind of that hump in the curve there. It's sort of, you think of it as like a barrier. Okay, that's a word we use to describe this a lot. It's an energy barrier, or a certain amount of energy that those reactants need to have in order to overcome that barrier and move on through the reaction progress and produce products. Okay, so that barrier, that difference in energy from where your reactants are starting to the peak of that curve, that amount of energy is the energy of activation. So we see that E sub A, that's energy of activation. Okay, and if your reactants collide and the amount of energy with which they collide is enough that they can kind of get over that peak of this curve, then they will proceed toward products. Okay, it's kind of like top thrill dragster. Okay, if you've ever gone to Cedar Point and you ride the dragster, okay, sometimes I've seen it, you know, it starts out and it has plenty of energy and it goes, you know, really fast and they go up and the roller coaster makes it over that curve and they go down the other side. I've also seen it where it starts out and it doesn't have quite enough energy. It's not moving quite fast enough, so sometimes it'll kind of get really, really close to that peak, but it doesn't make it over the peak, right? And the roller coaster slides back down and goes backwards. Either way, it's horrifying, and I have never ridden it, nor will I want to. I am not a ride warrior, okay? But I always think of Top Thrill Dragster whenever I see energy of activation curves, because it's kind of the same concept, right? Only the roller coaster is physics. This is energy in a molecular collision. Okay, so what happens with a catalyst, okay, and we'll talk more about catalysts again on the next slide, but if we look at this next diagram, we can see that purple pathway is another similar to what we see in the diagram on the left. Okay, that purple line in the right diagram is showing an uncatalyzed reaction pathway. So we see the reactants and products have the same amount of energy regardless of which pathway we look at, catalyzed or uncatalyzed. Okay, but we can see with the uncatalyzed reaction pathway, there's that huge energy of activation. Okay, with the catalyzed reaction pathway, okay, and this is what catalysts do for a reaction, okay, is they lower the amount of energy needed for that energy of activation, okay, or they kind of bring down that peak of that curve to a lower amount of energy. They decrease kind of the intensity of that energy barrier and make it a little bit easier for your reactants to have enough energy to turn into products, or they reduce the amount of energy that your reactants need to have in order to turn to products. Okay, so that's what catalysts do energetically. Okay, and on the next slide, we'll take a look at how do catalysts do that. What do they do with the molecules of our reactants that allows that energy of activation to be lowered? Okay, I think these slides are flipped out of order. I apologize. This is going back to when we were talking about reaction rates. Okay, again, we said if you increase the amount of reactants present, you'll have more collisions. Okay, if you increase the temperature, those molecules are moving at higher speeds, you'll have more collisions and you'll have more high energy collisions. Okay, so you'll get that reactant bond breaking happening more. Okay, and then we just talked about what a catalyst does to the energy of activation. Okay, it helps speed up the chemical reaction. It's not consumed. Okay, and the way that it lowers the activation energy is it helps with that orientation of molecules process, right? So when we talked about collision theory, we said in order for your reactants to collide and form products, they have to be arranged appropriately with each other, right? They have to be oriented a certain way for that collision to be successful. Okay, what catalysts do is they grab the reactants and they arrange them and position them correctly so that when they collide, that orientation piece is kind of already taken care of. You probably talked about catalysts in biology when you studied enzymes. Okay, enzymes are catalysts just in living organisms. Okay, they're biological catalysts. And so what they do, right, is they kind of help a biological mechanism occur because they take the two pieces that go together, rearrange them, right, and then help kind of with the production of products there. Okay, and chemically what's happening is they're reducing that energy barrier that the reactants need to overcome in order to turn to products. They're reducing or lowering that activation energy. Okay, so finally, let's talk about equilibrium. Okay, we needed to kind of cover that a little bit. In AP Chem, we'll get way more into reaction rates, okay, because there's a lot of, more nuanced stuff that goes on in that. But we had to cover that so that we can really understand more of what is happening with equilibrium. Okay, so what is equilibrium? Okay, we talked about this a little bit when we looked at vapor pressure. Okay, when we had properties of liquids, and then when we looked at colligative properties of solutions, we talked about vapor pressure. Okay, that happens at an equilibrium position. Okay, because what equilibrium means is it's the exact balancing of two processes that are opposite from each other. Okay, so when we looked at vapor pressure, that took place when you had an equal rate of evaporation and condensation within a closed system, right? If you have liquid evaporating at the surface and then condensing back down at the surface, okay, when those are happening at equal rates, we get what we call vapor pressure, and that's the amount of pressure exerted by the gas in that closed container. Okay, so we kind of have already seen this when we talked about vapor pressure, but now we're going to talk about it more in terms of reactants and products in a chemical reaction, right? Because vapor pressure is due to a physical change. Now we're going to look at equilibrium in terms of chemical changes. Okay, so far when we've looked at reactions, we have assumed that chemical reactions run to completion. One of the reactants will run out, right? We spent a lot of time talking about limiting reactant, theoretical yield, all that stuff. Okay, but it turns out in reality, a lot of reactions, especially gaseous reactions and reactions in aqueous solutions, okay, a lot of times those reactions stop way before the limiting reactant is completely used up. Okay, many of those reactions stop far short of completion when they take place in a closed system. So Again, limiting reactant is great in theory. In real life, a lot of reactions don't end up using all of your limiting reactant, right? That's one of those things we said that affects your actual yield, right? Sometimes your reaction doesn't go to completion, or you have side reactions going on, okay? So this is kind of applying that real life aspect to some assumptions that we've had so far. Okay, so when this happens, when you have a chemical reaction that does not run to completion, we call this a chemical equilibrium. Okay, so a chemical equilibrium is a dynamic state. What does dynamic mean? Dynamic means it's not stagnant, right? It can change. It's fluid. Okay, static is the opposite. Static means it doesn't change. Okay, but equilibrium is a very dynamic state where the concentrations of all reactants and products remain constant. Well, Ms. Supanich, you just said that dynamic means changing. How are those reactants concentrations staying constant? Well, they stay relatively constant, okay? And we'll see a lot more about this. You have some really, really great simulations in your OWL set, okay, that kind of help you visualize this graphically. But another thing that dynamic means here is we can change it, and the system will adjust based on what we change. So we'll look at that in 17.3. Equilibrium is a pretty cool topic because it's all about balance, which is kind of satisfying, okay? So what's happening in this dynamic state, or this state of chemical equilibrium, is you have your forward reaction. Okay, that's what we've looked at so far, right? Our arrows have always pointed from left to right. Okay, we've looked at reactions going in the forward direction. It turns out sometimes you can have the reverse reaction occurring at the same time. Okay, and to show that equilibrium, we use this special symbol that you see on your screen. Okay, that's like a double-headed arrow. Okay, that's the arrow that we use to show that we're in an equilibrium state. Okay, so you're going to start to see those in this chapter, and that just means that you have the forward process going like we're used to seeing. Okay, and then you can also have the reaction occurring from right to left. You can have those products reverting back into reactants, which is the reverse process going on at the same time. Okay, so that's a new symbol that we're going to see, very important. Okay, those are your equilibrium arrows. It's that double-sided or that double-headed arrow, but you'll notice it's not like a complete arrow on the ends. Okay, it kind of looks like two fish hooks pointing in opposite directions. Okay, that's your equilibrium arrows. Okay, so these first two bullet points are copy and pasted from the previous slide, okay? But what I want to do is I want to look at an example of this, okay? So let's look at this forward reaction, right? This is what we're used to seeing. You have two nitrogen dioxides combining to form dinitrogen tetroxide, okay? That's a forward reaction. So, this is the forward direction. It is possible that at the same time you have this combination going, it's possible that you'll have the decomposition reaction occurring going the other way, okay? At the same time that those two nitrogen dioxides are combining, you're going to have some of that dinitrogen tetroxide decomposing back into your nitrogen dioxides, okay? So if both of these reactions are occurring at the same time, the way that we would show this with an equilibrium arrow, okay, is we would say you have two nitrogen monoxides combining to form dinitrogen tetroxide while you also have the reverse process going on, okay, while you have that dinitrogen tetroxide decomposing backwards to go to our two nitrogen monoxides. Okay, so you can see we use that double-sided arrow to show both reactions are occurring at the exact same time. Okay, and I want to talk a little bit more about dynamic because again, you know, I told you it's a dynamic system. Oh yeah, but the concentrations of your reactants and products stay the same, okay? That's kind of like an oxymoron until we understand more deeply what that means, okay? So although an equilibrium system appears to be like nothing's changing, okay, it appears to be static, it is actually very, very dynamic at the molecular level, okay? And the reason that it appears to be static and the reasons our concentrations don't change is because there's no net change in the concentrations of reactants and products. Okay, you have the forward reaction occurring constantly, and you have the reverse reaction occurring constantly. Okay, so there might be like a little bit of fluctuation in the concentrations, but if you took like the average concentration of your reactants and the average concentration of your products, they would be very consistent throughout the state of equilibrium. Okay, so here's kind of our a diagram that we see to show this. Okay, here we would have water and carbon monoxide forming hydrogen gas and carbon dioxide. Okay, this is kind of like a single replacement, I guess. So you can see on that blue line, that's the forward reaction that starts to occur. Okay, once that starts to occur and we start to build up some products, then those products are going to start to go in the backwards direction and we'll get the reverse reaction occurring. Okay, and eventually what we start to see is you get a balance, or you get that equilibrium state where the forward reaction is occurring at the same rate as the reverse reaction. Okay, so you have a simulation in OWL today where you'll do some reactions and you'll set your initial concentrations of products and reactants, and you'll see how do those concentrations change as we get toward equilibrium. Okay, so that's it for 17.1. The OWL questions that you can do today, it's kind of a weird random OWL set. You can get through number 1 and number 39 today. Okay, so that's only 2 problems, and this was, only really a 20-minute lecture. So I really encourage you guys today, start skimming through 17.2. Okay, 17.2 and 17.3 are a little bit more beefy sections than 17.1, because clearly they make up most of your OWL set, comes from those 2 sections. Okay, so we'll have a little bit more difficult content tomorrow and Thursday. Okay, but 17.1 hopefully wasn't too bad. Start skimming through the rest of 17 in your textbook. I'll post more videos tomorrow.